We talked about some of the mechanical properties of DNA in Chapter 3 and described its chemical structure in Chapter 6. Here we turn to some of the mechanical properties of proteins. I like to begin with the density of a protein, which is typically given by around about 1.4 times 10 cubed kilograms per meter cubed. This would be for a condensed globular protein. Of course, a protein that consisted of many hydrophilic groups might in fact be extended in water and much less dense. It's useful to convert this number for the average density of a globular protein into a radius, so just solving using the volume of a sphere, 4/3 pi r cubed, the density to convert to a radius of a protein as a function of molecular weight, one derives then the following result. That the radius is the cube root of 3 on 4 pi, the molecular weight in units of Daltons, so that's relative to the mass of a hydrogen atom, and that turns out then to be 0.066 times the cube root of the molecular weight, and the units are nanometers. So for those of you who want to do atomic force microscopy, you can calculate the expected radius of an image using this formula. To give you a specific example, a typical protein may have a molecular weight of 100 kilodaltons, and this then would lead to a radius of 3 nanometers. Let's talk next about the elastic properties of proteins. The elastic properties of a material are described by the Young's modulus, shown on the slide as E, force per unit area, which is the stress on an object, is given by the Young's modulus times the strain, which is the change in length divided by length. We've talked often about spring constants, so of course depending on the geometry, but one can approximately take the area to be some characteristic length squared, in which case we can write F over L squared is E delta L over L, or then F is equal to E L delta L. You'll recognize this as Hooke's law, where this quantity EL plays the role of a spring constant. This table lists elastic moduli for several proteins. The units, as you can see, delta L over L is dimensionless, so the units are force per unit area, which is a pressure, so they're listed in gigapascals, that newtons per square meter. So you see 2 gigapascals, 2 times 10 to the 9 newtons per square meter, for a structural protein like actin, all the way down to 2 times 10 to the minus 3 times gigapascals for elastin, which is an elastic element of muscle tissue. Let's just look at some derived properties from this list. So if we take tubulin, which is a structural protein, it has a molecular weight of about 50 kilodaltons, which gives it a diameter twice the radius of about 4.8 nanometers. And the spring constant, if one then takes this as the L in this equation here, gives a K of around about 10 newtons per meter. If we take this softer elastin, from its molecular weight of 75 kilodaltons, we would estimate a diameter of about 5.5 nanometers. Putting this into this formula here for K then produces a spring constant of around about 0.01 newtons per meter. Turning now to the diffusion of proteins, let us consider again our typical 100 kilodalton protein, for which we had calculated the radius to be 3 nanometers. The friction coefficient from the Stokes's law is 6 pi r eta, and taking the viscosity of water at 300 degrees Kelvin then leads to a friction coefficient of 56 times 10 to the minus 12 newtons seconds per meter. The Einstein-Smoluchevsky relationship can then be used to calculate the diffusion constant as kT divided by this friction coefficient, and that then leads to a value for the diffusion constant of 73 times 10 to the minus 12 meters squared per second. Thus, our typical protein will move around about 8.6 micrometers in 1 second. Of course, as an RMS distance. The average distance will be 0. In fact, diffusion in the milieu of the cell is very different from free diffusion. The concentration of proteins is on the order of 400 milligrams per milliliter, and in fact, many proteins are actively transported along tracks. When the diffusion constant of proteins in live cells is measured using the techniques we described in Chapter 4, fluorescence particle tracking, it's found at short timescales that the diffusion differs from r squared proportional to dt. It's called subdiffusion because the dimensionality of the diffusion is drastically altered by the fact that proteins are diffusing through a dense matrix of other proteins.